In this video from ITFreeTraining, I will look at ICMP and command line tools that can be used in Windows to troubleshoot network problems. Understanding these tools allows the administrator to quickly fix network problems when they occur. Before I start looking at the tools available, I will first look at ICMP, or Internet Control Message Protocol. This protocol is used to transfer errors and control messages. In order to do this, the protocol uses datagrams, which are unreliable transmission. So to understand how ICMP works, consider that there are two computers on a network connected to each other. These two computers can send ICMP messages to each other. Since ICMP uses datagrams, these messages can be routed across the Internet. Some example messages are shown. ICMP messages can be used to test if a node is responsive on the network, a destination node is unreachable, and in IP6 used for router advertisements. The first tool I will look at is IPConfig. IPConfig does not use ICMP. However, it is one of the first tools that an administrator will use, as it displays the network configuration for that computer. To demonstrate this tool, I will first open a command prompt. Next, I will run the command IPConfig without any parameters. This gives some basic information about the configuration of the computer. There is one network adapter installed on this computer. At the top, you can see the configuration for the network adapter. If there were multiple network adapters installed in this computer, there would be one section for each network adapter. Each section contains configuration details about the network adapter. The first section is connection-specific DNS suffix. This allows the administrator to configure a DNS suffix to be used by that network adapter. As shown, this setting is configured in the Advanced TCP/IP settings on the DNS tab for that network adapter. This is useful if the administrator wants to use different DNS names for different DNS connections. The next configuration information shown is the IP6 address. Often an administrator will use IPConfig to quickly obtain information like the IP address of the computer. Below this is the link local address. Each network adapter will have one of these configured, and it remains configured for the life of the network adapter. These addresses will always start with FE80 and are used for local network communications like neighbor discovery. Notice at the end of the address is %11. This is referred to as the zone index. In Windows, this will be the same as the interface number. Later in the video, I will demonstrate how this can be used to ensure that a particular network adapter is used to transmit data. I will skip past the IP4 addresses, since this is an IP6 video, and next look at the gateway. Notice that the gateway address is a link local address since it starts with FE80. There is much debate over if a link local address should be used for a gateway or a unicast address. The advantage of a link local address is that if the unicast address changes on the router, this will not affect the nodes on the network. However, having a unicast address on the router helps with troubleshooting. It is up to the administrator to decide which address they want to use on their router. The next section down is ICTAP. ICTAP is an IP4 to IP6 transition technology. In Windows, it is disabled by default. In later videos, I will look at how to configure it. The next section is Teredo, which is an IP4 to IP6 transition technology that allows computers to connect to IP6 nodes when they are only connected to an IP4 network. Teredo in Windows is enabled by default. You can see that the IPConfig command gives the administration a quick overview of the network configuration on the local computer. To get more network configuration information, the administrator can add the /all switch. Some of the information is the same as shown when the command was run without any switches. At the top, notice that there is information about the computer itself, related to the computer, but not directly to any specific network adapter. Notice at the top is the host name, which is essentially the name of the computer, in this case WS1. Below this is the primary DNS suffix. When an attempt to resolve a single name is performed, for example, if an attempt was made to resolve NYDC1, this DNS suffix would be applied if no other DNS suffixes have been configured. The DNS suffix can be configured by opening the computer name settings available in System Settings. To access it, press the More button, and the primary DNS suffix can be configured here. This will, by default, be configured to the same as the domain name, so it is recommended that you leave it the same unless you have a good reason to change it. If I now go back to IPConfig, the next setting is the node type. This is configured to Hybrid by default. This setting determines how the computer will work with WINS when resolving names. WINS was replaced with DNS in Windows 2000, so on networks today, WINS deployments are rare, so the majority of administrators would have no need to change this setting. Next, there is IP routing enabled, which is configured to No by default. This can be enabled on server or client operating systems, which allows the computer to route traffic between different network adapters. The next option down is WINS proxy enabled. This is used to transfer WINS requests from one network to a WINS server located on another network. It is unlikely you will require this option to be enabled, as it is only required on a network where the node cannot access the WINS server itself, and it is unlikely nowadays that the administrator would be on a network with a WINS server to start with, as DNS has replaced the need for WINS servers. The next setting is DNS suffix search list. When an attempt to resolve a single name like NYDC1 is performed, the DNS suffix in this list will be appended. These options are configured in the advanced TCP/IP settings. In this case, there are no additional DNS suffixes that have been configured, so only the primary DNS suffix will be configured. That is it for computer-wide settings. If I scroll down, I will now look at the settings below this for the one network adapter installed on the computer. Some of the settings are the same as displayed with IPConfig without the All parameter, so I will not go through these again. The first new setting is the description. This is configured when the network adapter is installed and usually is configured by the manufacturer to tell the administrator what sort of network adapter it is. Below this is the physical address. This is essentially the MAC address of the network card. You can see that using the IPConfig is a quick way of obtaining this information. The next setting down is DHCP enabled. If the computer is configured to automatically obtain network configurations from the network, this option will be set to Yes. The next option is Auto Configuration Enabled. This is an IP4 setting that will configure an IP4 address when a DHCP server is not available. In IP6, it is not possible to disable auto configuration because it is necessary for services like network discovery. Below this is the IP6 address. This is the same address as shown when IPConfig was run previously with no parameters. However, notice at the end of the address is the word preferred. IP6 addresses have three states. The first state is tentative. This step checks the network for duplicate addresses. An IP6 address stays tentative only for a fraction of a second. It then becomes preferred. If you see deprecated, this means the IP address is in the process of being removed. So don't worry when you see preferred. It simply means that address has been checked for duplicates on the network and can now be used. Since an IP6 DHCP server is on this network, the next section is the DHCP lease information and when it will expire. Below this is the link local IP6 address. Like before, when IPConfig was run without parameters, the address has preferred at the end. I will skip past the next few settings as they are all IP4 settings and go down to DHCP6 IAD. IAD stands for Identity Association Identifier. This is chosen by the client. Unlike IP4 DHCP, multiple IP addresses can be assigned to the same network adapter. The IAD is used to bind these IP addresses to the same network adapter. Below this is the DHCP6 client DUID. This is generated by Windows using the MAC address as one of the inputs. Traditionally, a MAC address was used in DHCP to create reservations on a DHCP server. A reservation gives the client the same IP address each time. You may wonder why a DUID is required, but if you consider that nowadays a single network adapter can communicate over different networks, For example, a network adapter that is assigned for Bluetooth and wireless. A different ID may be required for both networks. This is not possible using just a MAC address. If the administrator creates a DHCP IP6 reservation, they will require the IAD and DUID. In the DHCP course, I will go into this in more detail. The last option is NetBIOS over TCP/IP. NetBIOS was developed in the 1980s. IP4 took over as the default protocol used on most networks. However, to access some network features, NetBIOS over TCP/IP was developed. This is a legacy option, so nowadays I would leave this option configured. If I have a look at the rest of the output, this shows the other network adapter settings for ISATAP and Teredo adapters. The settings are similar, so I will not worry about going through them. There are more parameters in IPConfig that are useful to look at when troubleshooting. The next parameter that I will look at is the renew parameter. This parameter will renew the current lease with the DHCP server. The process generally takes a few seconds. If the computer has not obtained an IP address from the DHCP server, this command will force it to contact the DHCP server. This is a good command to run if changes are made on the DHCP server. For example, if options are changed or added on the DHCP server. The next parameter is release. This command will contact the DHCP and release the current IP configuration. It essentially contacts the DHCP server and tells it that it no longer requires the IP address and it can be allocated. If the DHCP server cannot be contacted, the command will take a minute or two before it times out. Sometimes this command will need to be run on older computers when they are disconnected from one network and connected to a new network. This will force it to release the old network configuration, and then, if a renew parameter is used after this, this will force the client to contact a DHCP on the new network to obtain an IP address. In this case, I will not run the release command, as I do not wish to release my current IP configuration. The next parameter I will look at is display DNS. When this command is run, this will show the local DNS cache on the computer. Notice at the top is a DNS record for ssw.live.com. At some stage, this computer contacted this address and required the name to be resolved. Below this are the LDAP records. These are used by Active Directory. I removed this computer's ability to contact Active Directory before the demonstration, so notice that the computer was not able to resolve these addresses. Sometimes DNS records may change. For example, an IP address on a server may change. If the computer is having problems connecting to a particular server or services, it may be because the local cache has the wrong IP address. When this occurs, the DNS cache needs to be cleared, as otherwise the computer will continue to use the old address. To clear the local cache, use the parameter flush DNS. Notice that once the command is run, if I run IPConfig again with the parameter display DNS, no entries are shown, as all entries in the DNS cache have been cleared. In some cases, the IP address of the computer may change and the DNS server will have the old addresses. When this occurs, the parameter register DNS can be used. This will force the computer to register its IP address on the DNS server. However, for this to work, the DNS server must support dynamic updates. Notice that when the command is run, there is no indication that the computer was able to be registered in the DNS server. To check this, the administrator needs to check the local event viewer events for errors or check the DNS server. The next tool I will look at is the ping command. The ping command will send an ICMP message to another node, and the other node will send an ICMP message back. This is used to check that the network between the two nodes is working. In IP6, a zone ID can be added to an address. This is done by adding % followed by the zone ID. In Windows, the zone ID will be the same as the interface ID. Essentially, the zone ID makes sure the traffic leaves that interface ID. To understand the process better, let's consider that there are 3 computers on 2 different networks. The computer on the left has two network cards and thus is connected to both networks. I have added a simple link local address to each network card to make it easier to understand what is going on. If the computer attempts to ping a remote host using its link local address, in some cases the request may be sent over the wrong interface. In a lot of cases, IP6 neighbor discovery will work out which interface needs to be used. However, if it has not been able to find the other node, Windows will most likely use the first network adapter. Keep this in mind if you are using multiple network adapters and no response is received from a ping command. If this is the case, add % and the interface adapter to force the ping command to use a particular network interface. Rather than pinging an address, I will instead ping a domain name, in this case google.com. Notice that the ping command will work out the IP address of Google and ping the associated IP address. Also notice that the ping command will send 4 requests by default. Also notice that the end of the command is a time value. This is the round trip, in other words, the time it took for the message to be sent from this computer and return. The ping command is a useful command to get a quick indication of network congestion. In this case, the ping used the IP6 address. However, if I added the -4 parameter, notice this time the IP4 address will be used rather than the IP6 address. If the -6 parameter is added, notice the IP6 address will be used. A lot of commands that I will look at support the -4 and 6 parameters if you want to force the command to use IP4 or IP6. The next parameter that I will look at is the -L switch. This parameter allows the packet size to be specified. For example, if I ping Google with a packet size of 1444, notice that 4 packets are received. However, if I run the command again, this time with a packet size of 1445, notice that no response is received back, so it is not clear what happened to the packets in transit. The ping command also supports the -F parameter. This parameter prevents a packet being fragmented when it is sent. This parameter is only supported on IP4. When the ping command is run with the parameter -F, notice that the command reports back that the packet required fragmentation. However, this was not allowed. To understand how fragmentation works, consider what happens when a large packet is sent across the network. In order to get to its destination, the packet will need to go through routers. Each router will have a maximum transmission unit, or MTU, configured. If the packet is larger than the MTU, then the packet will be fragmented, which essentially means it will be divided up into smaller packets. The fragments will be reassembled at the other end, so in most cases will not present a problem. However, in some cases, fragmentation does cause problems. For example, with a VPN, part of the security of a VPN will use the previous packet as an input of the next packet. If a packet is fragmented, the VPN will think the packet has been tampered with and will reject the packet. Strange networking problems can happen due to fragmentation issues. If it does happen, it is just a matter of reducing the packet size so they are not fragmented. The next parameter I will look at with ping is -T. This will send an unlimited number of pings until the Control Break or Control C keys are pressed. If you are in the process of rebooting a server, this is a good command to run, as you will know when the server has started back up. If no ping responses are received for a long time, you know there was a problem rebooting the server. The next command I will look at is traceroute. Ping is a good command to quickly find out if there is a problem, but does not tell you where the problem is. Traceroute, on the other hand, traces the route to the destination, letting you know where the problems may be. In this case, I will attempt to perform a traceroute to google.com. You will notice that each router that the data needs to travel through is reported. Each router on networking is known as a hop. You will also notice 3 columns for the round trip taken from this computer to the router. This gives the administrator an indication of where there may be congestion on the network or of a possible network outage if the transmission stops at a certain point. By looking at the IP addresses, it would be hard for the administrator to determine where these routers are located. By default, traceroute performs a reverse DNS lookup. You can see for hops 1 through 5 and 12, it was able to determine this information. This does slow traceroute down, but gives the administrator an idea of where the hop may be. Later in the video, I will look at how to disable this feature, which will speed up traceroute. Notice also that hop 11 has asterisks recorded for the round trip. In this case, the router has not responded back. However, notice that traceroute was able to reach the destination of google.com. To understand why this happens, let's have a closer look at how traceroute works. To understand how traceroute works, consider that traceroute is run on a computer for a server that is 3 hops away. Traceroute will send an ICMP echo request to the server. However, it will configure the time to live, or TTL, to 1. Each time a packet goes through a hop, the TTL field gets reduced by 1. When it reaches 0, the packet will no longer be routed. This is done so that if there is a routing loop, packets do not go around in circles forever. When the first router receives the ICMP echo request, it will reduce the TTL to 0 and thus drop the packet. It will then send an ICMP time exceeded message to the computer. Traceroute can look at the IP address in the time exceeded message and will then know the IP address of the first hop. Traceroute will do this 3 times and report the round trip each time. The next step is to send a second set of ICMP echo requests, but this time the time to live is set to 2. This means that it will get to the second hop before the TTL becomes 0. The second hop will send an ICMP time exceeded message back. You can probably guess what happens next. The computer sends a third group of ICMP echo requests with the time to live set to 3. The third hop in this example is configured to drop packets and thus will not send any ICMP time exceeded messages. If you remember, when the traceroute command was run to Google, hop 11 had 3 asterisks for the round trip time and the address was given as request timed out. If the router is configured this way, or a firewall is configured to block the packets, it is not uncommon for a hop to not have any information returned about it. The last step is to configure the time to live as 4. This time the server will respond back with an ICMP echo reply. Traceroute knows that this is the last hop and thus the destination has been reached. You can see how traceroute works, but let's go back and have another look at it in action. This time I will run traceroute with the parameter -d and run it for google.com again. This parameter means that traceroute will not attempt to resolve IP addresses to DNS names. You will notice that the process is quicker than before. The downside is that you only get the IP address, so hopefully you recognize the IP address. Notice also that hop 11, like before, timed out. When you start working with IP6 addresses, they look complex at first. You can see that with these addresses, they all start with 2001 or 2404. This means all these addresses are global unicast addresses since they all start with 2 or 3. Following the 2 or 3 is the rest of the global routing prefix. There are only a few different addresses, and when they are looked up, they are all owned by the ISP I use and Google. Following this is the subnet ID. Only one of the Google addresses has a subnet ID, and all the subnet IDs from the ISP are all 1. When an IP6 address is registered, the organization that registers it is free to allocate the subnet ID as they see fit. In later videos, I will look at the subnet ID in more detail. The last part of the address is the interface ID. This is configured on the local computer. The organization has control over this address. So in this case, the path to Google goes through the ISP's network, through a number of nodes, and then goes into the Google network over a few nodes till it reaches the Google server. Once you start working more with IP6 addresses, you will start to recognize the different parts, and they won't seem that difficult. The next command that I will look at is pathping. Pathping combines traceroute and ping, which shows packets lost on the network. This can be useful to find where a network problem may be. When I run the command pathping for google.com, Notice that it starts much the same as traceroute. Hop 11 will once again not be able to be resolved. Notice now the command will pause for 250 seconds to gather statistics. The time is random, so when you run the command, the time period may be different. Rather than waiting that long, I will pause the video and return shortly. Running the command for 250 seconds allows the computer to get some accurate statistics of the congestion between the computer to the destination and also how reliable it is. On the left is the round-trip time. This gives you an average over the 250 seconds of the speed of transmission to each hop. To the right of this is the result of 100 pings sent to each hop. You can see in this case the connection is very reliable, so there are no dropped packets. However, if there was an intermittent problem, hopefully PathPing would highlight the problem hop by showing a lot of lost packets at that location. The next command that I will look at is netstat. Netstat shows the current connections to and from the computer. If I run the command now, notice that no connections are listed. Seems a little strange, but by default the command does not show ports that are listening. To show listening ports, add the parameter -a. You can see that there are a lot of ports listening, but there are currently no outbound connections. To create one, I will open Internet Explorer and do a Google search for MTU path. Once found, I will open their web page. MTU path is a free third-party tool that I will use later in the video. For the moment, I will save the file to the local C drive. If you are not able to find this page, I have added the link for it in the references of the video. I will now close Internet Explorer and run the command netstat again. Notice all the connections that are open now. These were required by Internet Explorer to locate the website and download MTU path. The next tool I will look at is MTU path. This tool works out the largest maximum transmission unit, or MTU, between your computer and the remote computer. I will run the tool for google.com. It does take a minute or so to complete, so I will pause the video and return shortly. Once complete, the tool will report the largest MTU that could be used, which in this case is 1444. If you remember earlier in the video, I used this value with the ping command. Now you know how I got this value. If you have an MTU-related problem on the network, the MTU path tool will allow the administrator to quickly work out the largest MTU size between 2 points. Otherwise, it is trial and error to work out this information. The last tool that I will look at is netsh. Netsh is a command line scripting tool. It allows network configuration to be performed on local and remote computers. There is quite a lot to this tool, but for this video I will only look at how to view the IP6 neighbors. Once I run netsh, this will take me to the netsh command prompt. In order to use netsh, the first requirement is to specify the interface that you want to configure. To do this, I will run the command interface IPv6 to access the IP6 interface. The next command that I will run is show neighbors. This will show all the known IP6 neighbors that this computer knows about. Notice at the top is an entry for stale. An entry will become stale if the computer has not been able to make contact with it for a while. There are 3 entries starting with FE80. These are the link local addresses on the local network. This is how IP6 knows which addresses are contactable on which interface. If the computer has multiple adapters and has not discovered the other nodes yet, you may need to add the zone ID to the address so Windows knows which adapter to use. Below this, notice all the multicast addresses. We know they are multicast because they start with FF. What is also interesting is that notice the MAC addresses on the right-hand side, listed here as physical address, for each of the multicast addresses. Each address starts with 3333. If you look closer, the interface ID, the right part of the IP6 address, is also present in the address. This is how multicast addresses are recognized on the network. Nodes of the network will inform the switches on the network which multicasts they can receive. Newer switches will recognize this and only send multicast packets to nodes that request them. Older switches, however, will broadcast multicast addresses to everyone. This gives you an introduction to how neighbor discovery works. There has been a lot covered in this video, so I will perform a quick summary of the main points. First, there was the command IPConfig. This displays network configuration on the local computer. This is a quick way for the administrator to find out information like the IP address and DNS addresses. Useful in troubleshooting to get a quick overview of the network settings. The next command was the ping command. The ping command is one of the basic tools that is used for troubleshooting. If there is a problem with the network, the administrator's first step is often to ping the other network. In a couple of seconds, the administrator can tell if there is a problem with the network between their computer and the remote node. The next command was the traceroute command. This provides the administrator with a list of hops between their computer and the remote node. This is useful for the troubleshooting process because it can pinpoint where a problem in the network may be. The next command looked at was path ping. Path ping combines ping and traceroute together. By gathering statistics over a period of time, this can indicate intermittent packet loss. For example, a hop lost some packets, but not all, which using the other tools may be difficult to pick up. Following this, I looked at the netstat command. This command gives a list of the open connections and can also show ports configured for listening. If your computer is infected with malware, this can help work out where the infection may be. Also useful for determining which ports the computer created when opening a connection. The next tool I looked at was MTUpath. This is a third-party tool that is freely available for download. The tool quickly determines the maximum transmission unit, or MTU, between the computer and the remote node. If you have a problem with packet fragmentation on your network, this will allow you to determine the maximum MTU size. It is then just a matter of changing your MTU size to this size. The last command I looked at is netsh. netsh is a command line configuration tool, which is a tool a whole video could be created on. It is useful for advanced configuration and advanced troubleshooting. Thanks for watching this video from ITFreeTraining. This is only one video in the free IP6 course, which is only one of the free courses available from us. Please see our YouTube channel or webpage for more videos. Until next time, I would like to thank you for watching.